The principle of uniformitarianism, foundations, evolution, and implications in earth sciences. The Earth is a planet of immense complexity, shaped over billions of years by countless processes: volcanic eruptions, tectonic shifts, erosion, glaciations, and biological transformations. Understanding how these processes operate and how the Earth has evolved has long been one of the most important goals of geology. Among the foundational ideas that guide this pursuit is the principle of uniformitarianism, a concept first clearly articulated in the late 18th century but still central to modern geological science. Uniformitarianism, often summarized by the phrase, "the present is the key to the past," posits that the natural processes observable today, such as sedimentation, erosion, volcanic activity, and tectonic movement, have operated in much the same way throughout geological time. This principle provided a radical departure from earlier interpretations of Earth's history, which often relied on catastrophism, religious doctrines, or speculative reasoning. In this article, we will explore the origins of uniformitarianism, its philosophical and scientific underpinnings, its evolution over time, and its profound impact on modern geology and related sciences. We will also consider its limitations and the ways in which the concept has been refined and integrated with newer ideas in Earth system science. Historical background. Pre-uniformitarian views. Before the 18th century, interpretations of Earth's history were dominated by catastrophism and religious narratives. Many scholars, particularly in Europe, relied on biblical chronology, which placed the Earth's age at only a few thousand years. Geological features such as mountains, valleys, and river basins were explained as the results of sudden, short-lived, and often divine catastrophes, such as the biblical flood. While naturalists observed layers of rock, strata, and fossilized remains, their interpretations were constrained by limited timescales and assumptions of divine intervention. As a result, geology lacked a systematic scientific framework. James Hutton, the founder of uniformitarianism. The principle of uniformitarianism was first clearly articulated by James Hutton, 1726 to 1797, a Scottish physician and naturalist often referred to as the father of modern geology. In his landmark work Theory of the Earth, 1795, Hutton argued that Earth's geological features were the result of continuous and observable processes acting over immense spans of time. Hutton's central insight was that geological processes visible in the present erosion, sedimentation, volcanic activity could explain the landscapes of the past if sufficient time were allowed. He famously described Earth as having no vestige of a beginning, no prospect of an end, highlighting the cyclical and ongoing nature of geological change. Charles Lyell and the popularization of uniformitarianism. Hutton's ideas were revolutionary but not widely accessible due to his dense and difficult writing style. It was Charles Lyell, 1797–1875, in his influential Principles of Geology, published between 1830 and 1833, who popularized and systematized uniformitarianism. Lyell argued strongly against catastrophism and provided numerous field examples demonstrating how slow, gradual processes shaped Earth. Lyell's work influenced not only geologists but also other scientists, including Charles Darwin, whose theory of evolution was partly inspired by Lyell's vision of gradual change over immense timescales. The core principles of uniformitarianism. Uniformitarianism rests on several interrelated assumptions. 1. Constancy of natural laws. The laws of physics, chemistry, and biology that govern processes today, such as gravity, fluid dynamics, and sediment deposition, have always operated in the same way throughout Earth's history. 2. Actualism in processes. The processes we observe today, for example, rivers eroding valleys, volcanoes building mountains, glaciers carving landscapes, have operated in the past, though their intensity and scale may vary. 3. Gradualism. Geological change generally occurs slowly and incrementally rather than through sudden, global catastrophes. Mountains rise, rivers cut valleys, and continents shift over millions of years. 4. Immense time scales. To explain the geological record, uniformitarianism assumes that Earth is vastly older than the few thousand years posited in earlier religious chronologies. This deep time allows small processes to accumulate into grand results. Uniformitarianism vs. Catastrophism. Uniformitarianism emerged as a counterpoint to catastrophism, but the relationship between the two concepts has evolved. Catastrophism emphasizes sudden, large-scale events, such as floods, asteroid impacts, or massive volcanic eruptions, as primary shapers of Earth. Uniformitarianism stresses the cumulative effects of slow, continuous processes. Modern geology recognizes that both gradual and catastrophic processes play roles in shaping Earth. For example, while rivers slowly carve valleys, asteroid impacts and massive volcanic eruptions have also dramatically altered landscapes and ecosystems. Thus, contemporary geologists embrace a modified uniformitarianism that integrates gradualism with acknowledgement of episodic catastrophes. Philosophical foundations. Uniformitarianism is not merely a scientific hypothesis but also a philosophical stance on how science should interpret evidence. Its philosophical contributions include empiricism. Observations of present-day processes serve as the foundation for interpreting ancient rocks and structures. Parsimony. Uniformitarian explanations rely on mechanisms already known to exist, avoiding speculative or supernatural causes. Predictability. By understanding processes today, scientists can reconstruct past events and predict future geological developments. This philosophy helped transform geology into a rigorous, empirical science rather than a speculative or theological pursuit. Applications in geology. Uniformitarianism has profoundly shaped many branches of geology. 1. Stratigraphy and sedimentology. Sedimentary layers, strata, are interpreted through principles of deposition observable today in rivers, lakes, and oceans. Uniformitarianism allows geologists to reconstruct ancient environments such as deltas, deserts, and reefs by comparing them with modern analogues. 2. Paleontology. Fossil assemblages are understood in the context of ecological and evolutionary processes still at work today. For instance, uniformitarianism underpins the interpretation of extinction, adaptation, and biodiversity shifts in the fossil record. 3. Geomorphology. Landforms such as valleys, cliffs, dunes, and coastlines are explained by processes like erosion, weathering, and sediment transport. By applying uniformitarian reasoning, geologists can estimate rates of landscape evolution. 4. Plate tectonics. Although unknown to Hutton and Lyell, plate tectonics fits neatly within uniformitarianism. The slow but constant motion of lithospheric plates accounts for mountains, earthquakes, and volcanic arcs through processes observable today. 5. Volcanology and seismology. By studying present-day volcanic eruptions and earthquakes, geologists interpret ancient volcanic deposits and seismic features preserved in the rock record. Contributions to the concept of deep time. Perhaps the most significant contribution of uniformitarianism is the concept of deep time, the recognition that Earth's history spans billions of years. Without deep time, gradual processes would be insufficient to explain geological formations. This realization not only transformed geology but also provided the temporal framework necessary for Darwinian evolution and modern biology. Evolutionary change, like geological change, requires immense spans of time. Evolution of the concept. From strict to modified uniformitarianism. In Lyell's time, uniformitarianism was interpreted almost dogmatically, only slow, gradual processes were considered acceptable explanations. However, as evidence for mass extinctions, asteroid impacts, and massive volcanic events accumulated, geologists modified the doctrine. Today, actualism, the idea that the same natural laws and processes apply across time, is widely accepted, but with recognition that the rates and intensities of processes can vary. For example, ice ages and glacial advances represent episodic but natural variations. Asteroid impacts, though rare, have caused dramatic and sudden changes, such as the Cretaceous Paleogene extinction. Supervolcanic eruptions and megafloods demonstrate catastrophic but scientifically explainable phenomena. Thus, modern geology integrates gradualism with episodic catastrophism, producing a more nuanced view of Earth's history. Implications beyond geology. The principle of uniformitarianism has had ripple effects in other disciplines. Biology. Darwin's evolutionary theory relies on gradual processes of variation and natural selection operating over long timescales. Astronomy. The study of planetary geology, such as the surfaces of Mars or the Moon, often uses Earth's processes as analogues. Climate science. Understanding long-term climate change depends on interpreting past climates using processes observable today, such as greenhouse gas effects. Archaeology. Uniformitarian principles help archaeologists interpret landscape changes and environmental contexts of human history. Criticisms and limitations. While foundational, uniformitarianism has faced criticisms. 1. Overemphasis on gradualism. Early uniformitarians rejected catastrophic explanations too strongly, which sometimes limited scientific understanding. 2. Assumption of process uniformity. While physical laws remain constant, the intensity and frequency of processes may have differed in the past due to unique conditions, for example, early Earth volcanism, lack of oxygen, asteroid bombardments. 3. Incompleteness of the geological record. Rocks preserve only fragments of history, making reconstructions inherently incomplete and dependent on assumptions. 4. Human-centric time perception. The immense timescales involved make uniformitarian reasoning difficult for human intuition, leading to challenges in communication and public understanding. Case studies illustrating uniformitarianism. The Grand Canyon, USA. The Grand Canyon's layered rocks and erosional features are explained by sedimentation and river erosion processes observable today, but acting over millions of years. The Deccan Traps, India. Massive basalt flows demonstrate that volcanic processes, while gradual in principle, can also operate episodically at immense scales, combining uniformitarianism with recognition of catastrophic intensities. Glacial landscapes of Scandinavia. Present-day glacial erosion and deposition provide insights into how past ice sheets sculpted landscapes during the Pleistocene ice ages. The continuing relevance of uniformitarianism. Uniformitarianism remains a cornerstone of geological reasoning. While refined to accommodate catastrophic events and variations in intensity, its central insight, that present processes illuminate the past, continues to guide research. In the era of climate change and anthropogenic impacts, uniformitarianism also offers a cautionary perspective. Processes like sea level rise, though gradual, accumulate into profound changes over decades and centuries, just as they have throughout Earth's history. Conclusion. The principle of uniformitarianism transformed geology from a speculative pursuit into a rigorous science grounded in observable processes and empirical evidence. From James Hutton's revolutionary insights to Charles Lyell's popularization, it provided the intellectual framework for understanding Earth's deep time and gradual change. Though once interpreted as strictly gradualistic, uniformitarianism has evolved into a more flexible doctrine that acknowledges both gradual and catastrophic processes under the same natural laws. Its influence extends far beyond geology, shaping biology, climate science, and even planetary studies. At its core, uniformitarianism represents a profound scientific truth. By studying the present, we can unlock the vast history of our planet and gain insight into its future.